Hello and welcome to this Room 2003 science topic that we are simply calling element addresses. The objective of this presentation, this video, is that by the time you are done looking at the examples and doing the practice work that go along with it, you will be able to write and read the address for each and every element on the periodic table. Yes, all 118. Now that doesn't necessarily mean that you will be writing or reading all 118, but that you'll be able to do that if at the end of this thing. So given any one of the 118, you'd be able to write and to read the address for that element. Now as we head into this thing, when we say element address, what we are referring to is this number code. And oftentimes in this code you will see that second number written as superscript, but occasionally you will see it written in normal format just as a matter of convenience. It's not always convenient to superscript things in whatever you're working in. So this 2s superscript 2 and 2s normal 2 are equivalent. They both refer to the same element address. And also in terms of the element address is unique. That 2s2 address only fits one element, in this case beryllium. And beryllium's element address is always 2s2 and only 2s2. Now a couple notes as we get started. Occasionally you will see E negative, which simply means electron. So when you see that symbol, just read that electron as electron. And secondly, as you go, because of the objective, please pause, rewind, and review these slides as often as you need to until you understand how to write and read element addresses. That is the outcome we are shooting for. So do these three things as much as needed. A couple connections I want to mention as we get going here. This activity connects directly with and is a spinoff of guided listening electron configurations. You may remember we did that last week, about midweek. And when we did that, we wrote the full electron configurations for select elements. So for example, carbon, this was the full electron configuration. And we're going to do more of these a little bit later on, but I wanted to do this element addresses thing as a way just to help reinforce and help practice some of the details of electron configurations. So with element addresses, we are going to practice writing and reading only the last term in an electron configuration. So for carbon, in our example, the last term, you have three terms here. The last term is 2p2. 2p2 is carbon's element address. And again, 2p2 is only carbon's element address. And let me emphasize too, although I didn't write this down, we are referring to atoms of elements in their ground state. So in their ground state, 2p2 only refers ever to carbon. Will be the last term in the electron configuration for carbon. And this last term is what we're calling the element address. The connection number two is simply this. As a way to think about element addresses, there are many ways to locate things on the periodic table. The first one we talked about was the atomic number. We know that the atomic number starts with 1 at hydrogen and goes through 118, the last currently known element. We can also locate by period and group. Periods run across, groups run down. We can also locate by special family, and we know there are 4 of those. And we can talk about the category, metal, metalloid, nonmetal. So element addresses is simply another way, or we can think of it as another way to specify where an element is located on the table, only in this case the reference is to their electron configuration or the last term in the electron configuration. So what you need to know to do this, to decode, to write, and to read element addresses, number one, you need to know the s, p, d, and f orbital blocks on the periodic table. You need to know the principal energy levels associated with each orbital layer block. And you need to know how position within each orbital block layer is indicated. Each of these things were things we covered in guided listening electron configurations, and we're going to review those now. I have the next 3 slides here. There's actually a handful of slides, a few more than 3, but let's review these 3 things. So the SPDNF blocks, these blocks are defined by quantum or wave mechanics. They tell us about the cloud space in which we can expect to find an atom's electron, and they tell us about the electron's energy. We'll do a little bit more with electron energy in later activities, but this is where the SPD and F blocks come from. So on the table, you get these 4 blocks that are color-coded. The yellow stands for the S block, and notice that helium is, because of its position, is a little bit out of place in terms of the block, but it is part of the S block. The yellow block, the blue block is the P, green is the D, and the gray block down below, kind of the orphans, are the F block. So you need to know those blocks. So learn those, tuck those away. With practice, you just kind of come to know them. Now the principal energy levels for the blocks. In the case of the S and the P block, they are convenient because they correspond to the period for the elements. So hydrogen and helium are in period 1, and their principal energy level is 1. Lithium and beryllium are in period 2, so the principal energy level is 2, and it carries on like so. So for the S block, principal energy levels correspond to period. For the P block, it's the same way. Only recall that the P block has no period 1 elements, so we pick right up with period 2, and that corresponds to principal energy level 2. And the P block carries on in that same correspondence, 2 through 7. Now the D block is a little different. The principal energy level shifts upward 1 unit compared to the period for the D block elements. So scandium through zinc are actually in period 4, but their principal energy level number shifts up to 3. And then we go 4, 5, 6. Actinium starts period 7, but actinium through this series they have a principal energy level of 6. And for the F block, the energy levels actually shift upward 2 units. So whereas these are in period 6, their principal energy level is 4. These are in period 7, principal energy level is 5. So we need to recognize the blocks, and we need to recognize these principal energy level numbers that are associated with each layer in each block. And then lastly, we need to recognize that position within an orbital block layer begins with 1 for the leftmost element and increases by 1 for each element to the right. And what that means is, like, this is layer 1 in the S block, so that is position 1. In layer 1, this is position 2. This is the 3rd layer, position 1, position 2. Second layer, position 1, position 2. And that pattern repeats as we go down through. So position simply is 1 with the first in the layer and goes upward from there. With the D block, it runs from 1 through 10, simply sequential, 1 through 10. But it does that for each layer in the block. So this would be 1 through 10, 1 through 10, 1 through 10. Now as we go here, what I want you to do, just to make sure you've got this position numbering scheme, is pause the video for a moment and answer these questions. What will the position numbers be for the P block and for the F block? So just take a moment and pause the video and answer that question, and then restart when you're ready. All right, so you're back, and you now know that the position within the P block layers ranges from 1 to 6 as we go across. And again, it doesn't matter which layer we're in, it's 1 to 6. And within the F block, as you counted up using periodic table, you know it ranges from 1 to 14. So those are the position numbering scheme. Now we're going to get into two writing examples, two reading examples, and then it's going to be your turn to work on your own. As we write and as we read, each address needs to have and will have these three parts. The first number is the number of the principal energy level. The sandwich letter is the block letter, and this is going to be S, P, D, or F. And the second number is going to be the block layer position number. So this number will range between 1 and 7, and this number will range from 1 to no higher than 14. It'll either be 1 or 2, 1 through 6, 1 through 10, or 1 through 14. But it needs to have, an element address needs to have these three components: number of the principal energy level, block letter, block layer position number. So writing example number 1 is the address for Neptunian. So I've copied the part of the periodic table with Neptunian in it. It's element number 93. And I always like to start with the block because we know the block drives the principal energy level in the D and the F block. So here we are in the F block, which means that this is principal energy level 4 and this is principal energy level 5. So the principal energy level for Neptunian is 5. And we've already mentioned the block is the F block, and the position number is starting with 1, 2, 3, 4. So the position number is 4. So the address for Neptunium, the last term in Neptunium's electron configuration, ground state electron configuration, is 5F4. So what about for tennessine? Tennessine, sorry, I keep putting an extra syllable. Tennessine. Well, here's the section of the periodic table with tennessine. And as I put the block up here, see if you can beat me to it. So the block that this is in is the P block. And with the P block, we know that the principal energy levels correspond to the period. So 2, 3, 5, 6, 7. So the principal energy level number for tennessine is 7. We've already mentioned that this is the P block, and it is in position number 5 within the P block, principal energy level 7. So its full electron address is 7P5. So those are the two writing examples. Now what about reading? So each address leads us to an element. So 2S2 is an element's address. And we've already used this, so I thought we would step through this example first. So again, starting with the principal, with the periodic table block, we've got the S block. It is principal energy level 2. So I already kind of zeroed in on principal energy level 2. And it is position 2. So position 1, position 2. So principal energy level 2, S block, position 2 leads us to beryllium, and only beryllium. Again, beryllium in its ground state. So where does 6D4 lead us? Again, starting with the block, because the block will drive principal energy level. Principal energy level 6 in the D block is down here. Remember, this is period 7, so the principal energy level shifts up 1, principal energy level 6. So 6, principal energy level 6 in the D block, and position 4 leads us to suborgium. 6D4 is the element address for suborgium in its ground state. And what about 4S1? Well, we know the S block is over here. We know in the S block that the principal energy level corresponds to the period. So that's principal energy level 4 within the S block, and it's position 1. So that takes us to potassium. 4S1 leads us to potassium in its ground state. So now it's your turn. Go to our Google Classroom and practice with this document, element addresses, and it is set up so that you can reattempt any problems you may miss. And again, refer back to this video as much as needed. Good luck, and I'll see you the next time.